So we are live, I guess. Okay, so good morning, good afternoon, or good evening. And welcome to the third International Colloquium on Physics for Society, jointly organized by the IUPAP and UNESCO. So my name is Kristin Dove, and I work at the European Spallation Source, so in Lund, in Sweden. And I'm also sharing the Accelerator Science for Society working group at the IUPAP, so the International Union of Pure and Applied Physics. And I will be moderating the event today. So the recording of our first two colloquia are now available on the Physics for Society webpage. So visit it and give us some feedback. So we were delighted to launch the series with Professor Anne Lhuillier, so on the International Day of Quantum on the 14th of April. So it was followed as a second webinar, so by a vibrant forum that brought together esteemed colleagues to reflect on infrastructure in Africa and the development of African light source. And today, so it's a great privilege to moderate this event featuring Professor Andrew Forbes, who is joining us live from South Africa to disentangle the quantum structure light for us. So he's a distinguished professor at the University of Witwatersrand, so WITS, as we would call it as nickname, so where he leads the world-renowned laboratory specializing in structural light and its application. So he's passionate advocate for photonics in Africa and the founding member of the Photonic Initiative of South Africa. And he's the director of the South Africa's Quantum Roadmap. So he's a fellow also of the SPIE, Optica, the South African Institute of Physics, and a member of the Academy of Science in South Africa. So before we begin, so I will invite my colleague to introduce this organizing structure. So representing the IUPAP, so we will first hear from Professor Silvina Ponce Dawson, President of the IUPAP and Professor at the University of Buenos Aires. Then on behalf of UNESCO, so Jin Zhao, who is Project Officer and Coordinator of the UNESCO Secretariat for the International Year of Quantum Science and Technology. She will speak on behalf of Dr. Amal, who is the Chief of Sector for Basic Science Research, Innovation and Engineering at UNESCO. So just about the format as well for today. So after we hear from them, we will have two sections. So one which will be reflecting dialogue, and then the other one which will enable everyone in the audience to ask questions. So you are warmly encouraged to participate and to write your question in the Q&A box, which is a question that's going to be answered at the end. So we can now give the floor to my colleague, so to Jin Zhao.
So, thank you, Christine. My name is Silvina Ponce Dawson. I am the president of the International Union of Pure and Applied Physics, IUPAP. We are very proud to have started this initiative in partnership with UNESCO to nurture a dialogue between the scientific community and the public in general. This is the third colloquium, as Christine mentioned, which began with a beautiful talk by Nobel laureate Professor Anne Lhuillier, followed by a discussion session on synchrotron light facilities, and which today continues with, I am certain, will be another beautiful talk by Professor Andrew Forbes of the University of the Witwatersrand in South Africa. IUPAP was created in 1922 with a few territorial members. Now it has about 60, as well as several corporate associate members. With this initiative, which will continue with 2 more colloquia in 2025, and hopefully with several more in 2026, we expect to advance with IUPAP's mission to assist in the worldwide development of physics and to help in the application of physics towards solving problems of concern to humanity. I want to mention another initiative that we just started within the framework of the International Year of Quantum Science and Technology, which is a photo contest. The details are announced on the IUPAP website. I invite you to visit the website to learn about all these initiatives as well as the future colloquia in the series. And now I invite Jin Zhao to speak about our partner in this initiative.
Thank you, Silvina, and thank you, Christine. Good afternoon, good morning, good evening to everyone joining us from around the world. Welcome to this third session of the International Colloquia on Physics for Society, jointly organized by UNESCO and IUPAP. My name is Jing, and I'm a project officer in the Division of Science Policy and Basic Sciences at UNESCO, and the coordinator of the UNESCO International Year of Quantum Science and Technology Secretariat. It is a great honor to open today's session with Silvina and Christine, and to warmly welcome you and our keynote speaker, Professor Andrew Forbes. UNESCO is really proud to have this special session to speak about structural light and commitment to quantum science capacity building across Africa. And UNESCO is proud to serve as the lead UN agency for the International Year of Quantum Science and Technology, which we are celebrating this year and hope to continue beyond 2025. And this initiative is part of a broader vision to promote science for peace and really develop a culture of science for sustainable development under the UN International Decade of Science for Sustainable Development. The Colloquia series really aim to create an open, inclusive, interactive, and interdisciplinary platform for knowledge sharing in quantum science and in physics in a broader sense. And together with IUPAP, we really want to bring together scientists, educators, policy leaders, and the young researchers, the next generation of innovators, to share cutting-edge developments and really share the insights on how quantum science can shape our collective future. Beyond these dialogues, UNESCO is also advancing several concrete actions in quantum science. For example, we're currently launching a global survey to map the quantum science research status and infrastructure to give a global view about the status. We are also issuing policy briefs on quantum science and technology, and that just this last week, we just published a policy brief on quantum science for sustainable development, and it's already open access on the UNESCO website. And we also support remote access to quantum labs and infrastructures within our remote access initiatives. We're also empowering young and women scientists through training on quantum coding. Also, we're working to combine quantum science with art and science, and to really integrate quantum into science education. And thank you very much for joining us today. And today's session is really part of this wider vision. And I really sincerely invite all of you to engage, ask questions, share ideas, and connect. Thank you again for joining us. Thank you.
So we invite now Andrew to give his talk.
Brilliant. Silvina, thank you very much, Christine, for the kind introductions. Let me share my screen and get this going here. I wonder if I can find a laser pointer. So let's see, I think over here. Okay, good, wonderful. So thank you very much for the opportunity to speak to everyone today, and good afternoon from South Africa. It's just after lunchtime here. In fact, it's a public holiday. We're celebrating Youth Day, so a very important event that happened that led towards our democracy. So it's a good time to speak about science and what we're doing in South Africa to use science to promote the well-being of society and to move the country forward. So the technical title of my talk is Quantum Mechanics with Patterns of Light. I'm going to, towards the end of the talk, go on to a little bit about our own research in this field. But I'm going to begin by taking a broader view, which is what are we doing in South Africa in the context of quantum. I'm from Wits University. I'll show a picture of that a little bit later. Hopefully all the people who are listening today know that it is the International Year of Quantum Science and Technology. It is a UNESCO-sponsored year. Many events happening all over the world, many in South Africa, very much an international flavor. And if you've not been to South Africa and you want to come out, we have nearly 100 events going on all over the country this year. So do reach out to us. We'd love to make it a little bit more international and engage you in that. But actually, quantum's been international for a little while now. depending on which survey you believe, lots and lots of money has been poured into quantum over the past decade, more or less. And this is one of the surveys showing the world map of all the countries who presently have quantum strategies. And here at the bottom of Africa is South Africa. We also have a national strategy in quantum, definitely not in the billions of dollars, unfortunately, but locally it's impactful money, and we've been able to do something useful with that. So let me use our quantum strategy to introduce you to South Africa and a little bit about what we're trying to do here. So here is South Africa at the bottom of the continent. If you come down to the south, you find Cape Town. It's a very beautiful place to visit if you like mountains and the vineyards. And there we have a node that's working on quantum devices, making homemade technology that can be plugged into quantum communication systems. If you go a little bit inland, you find Stellenbosch. It's a university town, really in the heart of the winelands, very, very beautiful area of the country. And there we have a group working on quantum sensors, trying to solve real-world problems that are relevant to Africa, for example, detecting malaria. If you go a little bit up the coast, this is where I grew up. It's Durban. It's a surfing town. For a very long time, I would say at least a couple of decades now, they've had a very strong program in quantum computing, and they continue to do that under the national strategy. And if you come further up the coast, it actually gets warmer and warmer as you go north. You hit Zululand. It's a wonderful place if you like safaris. And there we have a group looking at quantum sources and quantum dots and how they could be used for single photons and for sensors. And if you come into the middle of the country, you find Johannesburg. It's where I'm based. It's actually the largest man-made forest in the world. Wits is an inner city university, and in my group, we play with quantum optics. So we use optics as our platform to do things like communication and imaging predominantly. So you see that we have actually 5 nodes around the country that are sponsored under our Quantum Future, under our South Africa's Quantum Technology Initiative. Of course, we have activities all over the country, not just at the 5 nodes. We've been running about 100 events over the last 3 years, ranging from advocacy to flagship projects all over the country at different centers, trying to grow a quantum community. So we had about 3 years of funding. It just came to an end now. And in those 3 years, I'm not going to read all the numbers to you, but essentially we've been distributing our energy across things like gaining critical mass, then using that critical mass to produce good science, so, nice journal papers, but also a focus on technology. We want to transition from science to technology to grow a quantum economy for South Africa. We have a very high unemployment rate. We'd like to see if we can address that through technology developments. So lots of technology developments and industry engagements. If I focus a little bit behind the numbers, what's going on, as I said, we need to grow a community. So unlike many developed countries where you already have critical mass, and now it's just a question of what should the people do, here we have to find the people and nurture them and bring them forward into the quantum world. So here's Isaac. We have a program to find emerging quantum leaders and support these young people to become our future quantum generation of scientists. So critical mass is central to our national strategy. On the science and technology side, it's all about data, I guess. You can think of, we have metrology as collecting data in a more precise way. You can think of quantum communications as moving that data around in a fundamentally secure manner. And then the computing might be thought of in terms of data processing. So what do you do with the data now that you have it? So these are the 3 themes that we're working on under our national strategy. It's pretty similar to other people. It's just that because we have limited resources, we need to focus a little bit more strategically on how we use or place our money in order to maximize the impact. So for example, we've decided to focus on metrology as one of our central themes, to try to make better sensors, and as I said, to make them relevant to our own internal problems. For example, a very sensitive sensor for malaria detection to show that quantum technology can make a difference to the people and not just nice science. So we have lots of people around the country trying to work on developing new metrology and sensing devices. On the communication side, our strategy says that we really want to show the local commercial sector what quantum communication technology can do. So we want deployable technology that will fast track the commercial uptake. And with this deployable technology, we want to, of course, plug and play our own homegrown technology into it. So this is more a platform to show people why they should embrace quantum. And then on the computing side, we don't have the money nor the people to build a quantum computer. And so a long time ago, we decided we'll concentrate on quantum software that will be agnostic to which computer it's running on. So quantum software is the way that we're going. We support many, many programs to write apps that are specific to industries, for example, to the financial sector or the logistics sector, using commercial quantum computers that are available on the cloud. And in all of these endeavors, of course, we have to engage industry. Otherwise, we really won't be able to get any deployed technology out there or any uptake by the commercial sector. So we have many, many companies around South Africa that are working with us. It takes a lot of effort to do that. Anyone who's tried to do that will know very, very well that industry doesn't give you their money for free. And it takes a long time to get them to understand what it is you're trying to convince them of. But now we have a bit of critical mass in our partnerships, and that helps tremendously in terms of showing the government why this investment is worthwhile. And these are, of course, all established companies that are already out there, but not quantum, but slowly embracing quantum. We've also seen the first 4 startup companies from within our own technology. These are still very fledgling entities with only a few employees each. They all have different focuses, from imaging to sources to detectors. But it's very promising to see that after just 3 years of funding that we already are starting to see the sprouts of science going through to technology and technology going through to commercial entities. So the good news is that we have just secured the next 5 years of funding from the government. That will take us to 2030. And in very broad brushstrokes, what are our plans? Well, we want to strengthen the centers we already have. We want to establish new quantum centers over the next 5 years. So more nodes. Hopefully next time I speak at one of these sessions, it won't just be 5 quantum nodes, but many, many more. We want to see fully deployed quantum technology in each of our 3 themes, where we can show somebody's really using it now and not just playing around with it as a toy. We'd like our startup entities to become really commercially viable companies. And we want to double all the engagement with industry and the co-investment that we get, because this shows the government that we really are not training students, but that we're training a quantum workforce, and that our goal is to move towards a quantum economy for South Africa. So that's in a nutshell what we're doing in South Africa in the past and looking forward to the next 5 years. And I'm totally open to questions at the end of the session to explore that a little bit more with you. Now I'm going to switch gears a little bit and focus on specifically our node and what are we doing. And because of the limited time, I'm going to pick only one example within it to show you a little bit about how we could start off with cool science, and hopefully the science becomes technologies of the future. So as I told you at the very beginning, I'm based at WITS. So here it is, it's inside the city. This is the Great Hall. And a little bit behind these trees is the School of Physics. And inside the School of Physics is my lab, and my lab plays with structured light. So what do I mean by structured light? So think of it like this. Light has got many degrees of freedom. And what we want to do with structured light is identify those degrees of freedom, try to harness them, control them, and then we can use them both for fundamental science and for applications. What you see in the little animation that's playing in front of you is an experimental video played off a simple data projector. Inside a data projector, you'll find a digital micromirror device. And here we're controlling the amplitude and the phase of light. This is classical light. I'll switch gears to quantum in a second. But these are very familiar degrees of freedom. What we try to do is to identify more abstract degrees of freedom. Now I'm going to give you an example in today's talk about how you can find topology that's hidden inside light. So think of it as controlling light's degrees of freedom. And it's not just pretty pictures. It's really to challenge your paradigms, look beyond the obvious, and try to harness the potential that light really has that perhaps you're not tapping into. So you might wonder, well, why bother, particularly in the quantum realm? Because, you know, if you've been watching the news, then Yasira, my former student, has a very nice paper out with her Chinese collaborators, and they have a link that spans nearly 13,000 kilometers via a satellite from South Africa to China. So this is quantum key distribution and uses polarization. So if you can go so far and so fast, why bother with new degrees of freedom? Well, polarization is fantastic. It works in many, many channels. But in terms of the optical potential, it's just a two-letter alphabet. You know, it's horizontal or vertical or left and right. You have two options in your encoding scheme. What can you do with the patterns of lights? Well, to answer the question, let's imagine that we have a beam of classical lights, and I just put my hand in front of it and I tap off a 1 square millimeter part of light. So I have 1 by 1 millimeter blob of light over here, and I ask the question, how much information can I pack into that square millimeter? And in particular, how many patterns of light can I pack into it? Well, if you do the calculation at optical frequencies, the answer is millions. You can pack millions and millions of patterns of light into that square millimeter. Of course, the challenge is how to do that. Well, if it has the capacity of millions and millions of patterns, you can imagine that if each of those patterns were an alphabet, then you have an enormous encoding alphabet, way beyond the two-letter alphabet of polarization. And the idea in structured light is not to abandon polarization, but to enhance it with these new degrees of freedom, the structure of the light itself. So in today's talk, we want to say, could we do this at the quantum realm? So let's go into the quantum lab. So here's Berenice with a quantum experiment. And what we're going to do is we're going to zoom into the little crystal that's producing our entangled photons that we're going to use as our resource for quantum structured lights. And I'm assuming that not everybody in the audience is a quantum physicist. So let me give you a few slides of tutorial to explain how that works. So we zoom into the lab and into her specific device. And over here, she has a non-linear crystal. It's about 5 millimeters in length. And what we're going to do is we're going to come in with a high energy photon, in fact, a green photon, which is why you see the green glow around the lab. And if we engineer the phase matching correctly, we can go out with 2 lower energy photons. And I can show you that if the phase matching is done correctly, the 2 photons going out will be entangled. And so you have entanglement as your resource. If I zoom into those 2 photons, what do I see? Well, we know that the quantum world is random. So if you watch any one of these little blobs, imagine it's like a magnifying glass watching the photons, you'll see that the arrival of the photon is completely random. But if you watch the 2 magnifying glasses together, you'll see that the joint arrival is not random. So watch this. Of course, it's just a little animation. The photons are arriving randomly. Each photon is random on its own, but jointly it is not random. So I'll play it again. If you watch them together, you'll see that if you know the position of one photon, you know the position of the other one. In fact, this type of entanglement is naturally in a spatial basis. In this case, it's in the position basis. So random on each arm, but not random jointly. And I can exploit that because if I already have spatial entanglements, well, I can use my spatial entanglements and just change the basis. And I'm going to change the basis to patterns of lights. So rather than pixels, I'll use patterns. They have many, many indices. My favorite one is this angular index, which gives you orbital angular momentum, and that gives you this twisted light that's coming out. So all I'm going to do is change my basis. So to change the basis to this angular structure, what I'm going to do is I'm going to take my blob of light, like my laser pointer. It has got no angular momentum. It's got plane waves, and I'm going to give it a little twist. So I'm going to give the phase a twist in the azimuth to get this twisted nature. And when I do that, I have 1 h-bar per angular momentum of each photon. And this is an orbital angular momentum component. I can twist it once, or twice, or 3 times, and so on, all the way to infinity. You see that after 3 twists, I have a large orbital angular momentum per photon. I have a Fusili-Pastor type wavefront, and I have a ring of light as my structure. And I can twist not only in the clockwise, but also the anti-clockwise direction, in which case I get negative h bar per photon, again going up in twists as I twist stronger and stronger. So orbital angular momentum is a wonderful basis. It's a form of structured light. It can go from minus infinity to plus infinity, at least in principle. And these are the kind of digital holograms that would produce this type of twisted nature. So how could I use this in the quantum lab? So let's go back to my little cartoon. This time I'm going to be a little bit more specific. So here's my crystal. I'm excited with my high energy photon and out of my 2 entangled photons. And now I'm going to tell you that I'm specifically going to excite it with a photon that has no orbital angular momentum to begin with. So its value is 0. Well, orbital angular momentum is conserved. So now it becomes a primary school math question. How many different ways can you add 2 numbers for these 2 photons to 0? Well, there are an infinite number of ways. Photon A could be +1, in which case photon B will be -1. That adds to 0. That's a possibility. Or vice versa. Or photon A could be a value of 2h bar, in which case photon B is -2h bar. That also adds to 0. And so on. You get the idea. In fact, there are an infinite number of possibilities. So if I write down the quantum states, now to get rid of this. How do I get rid of all this stuff now? Sorry, I've just gone. Okay, there. So if I write down the long states, I have the 0, 0 term, the +1, -1, the -1, +1, and so on. And so I have a very, very large Hilbert space. In fact, this Hilbert space allows me to do quantum mechanics with patterns of light in a very large dimensional space. And large dimensions are very useful because you have more bits per photon, you're more tolerant to noise, you have a lower chance to clone, many, many advantages. So this quantum state is entirely in the spatial structure of light. And to detect it, all I have to do is run my classical toolkit backwards. So here's Angela. She's using a digital toolkit to produce in a long exposure this orbital angular momentum beam with a ring of light. If this were a photon coming backwards through her system, I can use the reciprocity of light to detect it. And that's all I need in my quantum lab. Detect my 2 photons with the digital toolkit. And if you do that, then you can access very, very high dimensional spaces. So a lot of work by many, many different groups around the world over many, many years have pushed the dimensionality up very high, as you can see by the little insets, novel ways to detect with just 2 mutually unbiased bases or Bell measurements, or today even with cameras where you can photograph entanglement. You can photograph the structure of entangled photons. So fantastically beautiful research out there, very exciting direction to go into. Well, what I showed you now is the structure of light in its phase, because the orbital angular momentum was this twisted light. If I add 2 twisted beams together, so have a look at this. Here's my blob of light, my laser pointer, with no twist, and I add to it an orbital angular momentum beam with 1 twist. But I add them with orthogonal polarizations. So one is left circularly polarized and one is right circularly polarized. What do I get? I get a beam that is structured in its polarization. So rather than talk about light having just horizontal or vertical or left and right, this beam has got every possible polarization built into it all at once. And you can see how that could be very, very useful for metrology and sensing. And I can do the same thing at the quantum realm. All I have to do is make sure that one of the photons, let's say photon A, lives in the space of spatial modes. So here there are 2 spatial modes. And photon B lives in the space of polarization. So here it is, right and left circularly polarized lights. And this hybrid combination will give me this hybrid polarization structured states. So if you were to think about block spheres and where they live, one photon is living in a space of polarization, the other photon is living in a space of spatial mode or patterns of light. And now it is this weird hybrid mix of two different degrees of freedom. And that's proved very, very powerful. You can put it down optical fiber or in free space. It gives you a new encoding alphabet for communication. You can do teleportation with many, many different degrees of freedom, as a few Chinese groups have been doing. You can do ultra-sensitive rotation measurements, so imaging and sensing. In this case, it's sensing specifically. That is very powerful. And then imaging. You can start to image living systems by probing the birefringence with the polarization photon and the spatial structure with the other degree of freedom all mixed together. And so you see beautiful high contrast quantum images, in this case of a zebrafish. So hybrid entanglement opens up many, many avenues for exploration. What we've been doing recently is to explore a hidden degree of freedom inside this light. And I'm going to use this as the example to show you the power of structured lights. So here's my hybrid states with all the different polarizations inside it. And because it's got all polarizations at once, it means that if I map it to the Poincare sphere, which is the space in which polarization lives, I'm going to wrap that sphere once over. Just to repeat that, because the beam's got every polarization and the Poincare sphere describes polarization, if I were to map this across to the sphere, I will wrap the sphere once over. The little arrows just represent the polarizations, pointing upwards if it's right circularly polarized and pointing downwards if it's left, and so on. So I wrap the Poincare sphere once over. This is a mapping from one space to another. When you have a mapping from one space to another, it defines a topology. And the topological number is how many times did you wrap that space. So now I can go to my quantum states. It naturally defines a topology. Photon A is real space. So if I measure everywhere on photon A, I will collapse photon B to its particular polarization, but the state has got every polarization. That means that if I measure everywhere on photon A, I must wrap the sphere of photon B once over. And so this means I have a topology. And this topology is actually called a skyrmion. And so we show it here as the spin textured field. It means, and let me go to the next slide to show you, photon A has got no topology. It just lives in a world of patterns of lights. Photon B has got no topology. It lives just in a world of polarization. Where is the topology? The topology sits in the entanglement between the two photons. And you can go to the lab and confirm this. So here you see the wrapped spheres that I was showing you earlier as kind of cartoons. These are now experimental images. And what you see is that we can create these tailored quantum landscapes in polarization in space. And why is that powerful? It's powerful because if I make a quantum state that has only one wrapping, so a topology of one, this is what it looks like, it can never leave the box of one wrapping. And if I make a state with three wrappings, here it is, it can never leave the box of three wrappings. So they can never cross over. If I introduce noise to my system, this state should stay topologically stable. So that's what we've been studying recently. We've been studying this idea that could you make quantum states where even if the entanglement is slowly decaying, the topology remains intact. And if the topology remains intact, you have an encoding alphabet that should be robust to noise. So the question is, what type of channel, quantum channel, would be robust to noise? So here's my topological quantum state. I'm going to send it through a noisy system. The entanglement might decrease, but the topology shouldn't. And so we've been studying this year. And let me give you just one example. So on the horizontal axis is the quantum contrast. If you don't know what that is, imagine that on the left-hand side, it's very pristine entanglements. And as I go further and further to the right, it becomes less and less entangled. And if I watch the traditional quantum measures, which are all these dashed lines, you can see that all of them decrease as the entanglement gets worse. Well, that's not very surprising. That's what most entanglement systems do. But look at the topological alphabet. That is a solid line. It stays absolutely constant all the way until the entanglement vanishes. So this is an encoding alphabet that is completely resilient to noise. And so this is more an open statement of challenge rather than achievement, because now the question is, how could you harness a topological alphabet based on the structure of light to make your quantum communication or your quantum computing immune to noise? So I'll leave you with that question. I just want to end with two quick notes. The first one is that what I've shown you in this very brief example of the power of structured light is how to use the structure to make things robust to noise. But you can do exactly the opposite. You can say, let me make the structure very sensitive to noise. For example, my twisted light, I will make it highly sensitive to the noise. That way I can use the structure of light as a probe for the medium that I pass through. And this can be very, very powerful for sensing and computing. So for the students in the audience, whenever people give talks, it always makes it sound like the topic is complete and everything is known. Well, here's my little jigsaw puzzle. And if you just look at the numbers of what has been achieved so far, you'll see that the numbers are pretty low. In fact, in structured light, the bits per photon or bits per second is nearly zero, and the distance we've managed to travel is also nearly zero. Zero compared to how far you can go with polarization. So there's an enormous amount of work to be done to truly harness the structure of light and take it forward into real technologies. And then if you look at the dimensions that we've controlled, well, we've pushed it very, very high, up to hundreds of dimensions, no problem, but only with 2 photons. And if you look at what about how many photons have you controlled? Well, many, many photons, but only in 2 dimensions. So the diagonal, where you have many photons and many dimensions, this red square is almost completely empty. I could count on one hand how many studies sit here at this interface. So there's a massive gap in our technological landscape that we need to fill if we're really going to move forward with quantum structured light. So that was a very brief introduction to South Africa's quantum roadmap and a little bit about the research that we do. All the experimental results that I showed you are from my team. I always have to thank them because they're the ones who do all the beautiful experiments in the lab. And then I'm going to come to an end, and thank you very much for listening because my time is up. But please do reach out to me if this has been a little bit too fast for you and you want to know more details. I'll be very, very happy to share it. So once again, thank you for listening, and thank you to the organizers for inviting me.
Thank you very much, Andrew, for the beautiful talk. I don't find the applause symbol right now on the Zoom. So let me ask you a few questions I thought of, but I will interlace them with some of the questions that the people have already put in the Q&A window. I invite everybody to put their questions there. And so you address 2 topics. On one hand, the science of structural light and the possible eventual technological applications. And then you also talked about the quantum initiative in South Africa. And so with respect to that last item, I wanted to ask you if you, because you have past experience advancing photonics in Africa, not just South Africa, if there are any ideas of advancing with a roadmap in quantum science and technology all across Africa. And in particular, Muna said also asked if there are internship or research collaboration opportunities with students from Africa. So what's the idea about enlarging this initiative to include other African countries?
No, it's a great question. And to be dead honest, in the first 3 years, we certainly were very inward focused as we got our own house in order and established our critical mass at different centers. Now that we've done that, in the next 5 years, we're able to look outward a little bit. So in fact, the week after next, we have a gathering down in the south coast of Durban with all the leaders of quantum initiatives, either established or hoping to get established in Africa. And the idea is to coordinate a program to move forward with. So to look at how we could work together, how we could help one another, how we could learn from our good experiences and our bad experiences. Now, in the photonics world, we've been doing collaborative projects and hosting students and researchers for many, many, many years. And so we have a very large network and a lot of experience on how to do that successfully. And the plan is to translate that across to the quantum world. So it is certainly part of our plans. And I believe I can speak for everybody when I say that I doubt that there are any African quantum leaders who would not embrace the same idea. So watch this space, and hopefully if you all ask us to speak again in a year's time, we will have many cross-country initiatives that bind the continent together.
So in relation with that, you know that we are in the middle, well, it just started actually, the International Decade of Sciences for Sustainable Development, which one of the aims is to highlight the role of science in addressing global challenges and promoting sustainable development. Now, your work is at the intersection of advancing quantum science, but also capacity building in Africa. And so how do you think that quantum technologies and photonics will contribute to the goals for sustainable development in Africa? And how do you think that the quantum divide between more or less developed regions can be, I mean, could science contribute to reduce that divide?
So I think quantum technologies can make a direct impact. Certainly, we are looking at technologies that solve real problems. I gave the example of malaria detection as one of them. We're supporting a lot of biophotonic type initiatives for health problems. We have quantum computing expertise and people working on climate change problems. In South Africa, we have a large unemployment problem. So we are hoping that quantum could be an economic solution, so make an economic impact by employment of young people. I'm a firm believer that beyond the direct quantum applications, there's also what I call quantum-inspired applications. And we've already seen much of this already. For example, we've used our quantum imaging work to solve societal problems in the crime prevention world. The solution was not a quantum problem and not really even a quantum solution, but it required all the techniques and expertise of quantum. So I think that what we need to do is we need to look at how we could use our skills that have been developed in one sphere and apply it more broadly beyond that. So I believe that the direct and the indirect benefits will be huge if we just open our minds to how we could use our skills and not concentrate only on publishing beautiful science papers. As for the divide, I think right now people are very much inward focused, but as technologies mature, they will have to look outward. You cannot have a global quantum network, for instance, if half the planet is not part of that network. It simply doesn't work. Would be the same as connecting fiber only to certain countries. So I think it will be a forced connection at some point, but hopefully scientists begin to communicate and share knowledge long before that. I think there's a willingness in the developed world to engage with the developing world, and this workshop I mentioned in a couple of weeks' time involves a very large delegation from Germany, for instance, who are coming out to look at how they could engage more fruitfully. I think we need to have more dialogue and we need to have more meetings across the boundaries, not just within our little spheres of influence.
Thank you. So let me move a little bit to the science. You talk quite a bit about this new way of encoding information, which looks very interesting because it's very resilient to noise using structural light. You also mentioned the limitations. So there is I wanted to ask you, how do you envisage the future of communications with the use of these new technologies. And also, I would like you to answer another question that was posed in the Q&A window, which asks, what kind of information will be inserted in the patterns of light, which are 1 millimeter of area, and why? That's a question from the audience.
Well, in the classical world, you could use the patterns as sort of independent channels or pipes of information. So imagine that you modulated the light with your standard method, and then instead of using single mode fiber, for instance, single mode means one pattern. Imagine that you could have 1 million patterns down the tube. Well, then each one would hold its own information. So that would be mode division multiplexing. Or you could actually modulate the patterns themselves. They could directly form the alphabet. So there's many, many protocols where you could exploit it, either directly or indirectly. All of them promise huge information capacity per photon. It goes like the log of the dimension. In the quantum world, we have all the protocols. We know how to do it. The problem is that the technology is not quite there yet. So we don't have transmitters for 1 million patterns or detectors for 1,000 dimensional quantum states. I would say that the dimensionality is harnessed in the time domain. So we can get to high dimensions by modulating in time. This is very standard, but in the spatial domain, not so much. So the potential is huge, but we need the technological pieces to be put in place.
Thank you. So you talked also about the need for global communication, and you know that nowadays it's not so easy. I mean, the international scientific collaboration is being a little bit, I don't know, jeopardized by measures, in particular in the area of quantum science and technology, which is considered as a type of technology that that some governments don't want to share with other governments, basically, so that there are restrictions. So how do you see what the scientific community could do to keep on having this collaboration and maybe convincing government of collaborating in this regard? And let me ask you also include a question from the audience that says, in an ecosystem where major economies are pouring lots of money into quantum science, in which spaces do you think South Africa can compete now and in the near future? What are the strengths that you see as unique to South Africa? So there is collaboration and there is competition in the question.
Yes. Well, let's start with the second question first. And I think the example of our quantum computing strategy maybe highlights the way we think. So we realize that we do not have the money or the people to build a quantum computer. And even if we did, I think that it would be highly unlikely that we could be successful against the other companies who are already doing it, PsiQuantum and IBM and many, many others. I mean, they're just so advanced, it's hard to see how you could realistically compete given our resources. And so we make a strategic decision not to build a quantum computer. And the example I like to give is your smartphone. You don't have to be building smartphones to be part of the smartphone economy. You could build apps that run on smartphones, the likes of WhatsApp and Facebook and whatever your favorite TikTok app is. And, there is a lot of economic value, and you can participate in the economy in a very meaningful way without ever having to build the electronics. So that's how we see our benefit and our impact in the quantum world. It's this sort of intelligent use of resources and very careful placement of those resources in order to participate in the coming economy. So we accept that we will not be part of all quantum economies, but we can be part of some, and we have to make impact there. In terms of the sharing, I mean, there is the competitive side, which is the commercial part, but scientists naturally do tend to share. And I think it will come down to organizations like IUPAP and many others to try to keep the dialogue open and neutral and not politicized. We know that if we really are going to have a globally connected quantum network, or we're all going to participate with quantum technologies, there will be no such thing as some people having it. You can't have some people connected with fiber optics. Then you might as well have nobody connected. If you're going to connect your banking system to me and I'm not secure, then you're not going to be secure either. So there is mutual benefit in sharing. And it's for the big societies to work with scientists to be their voice. I mean, you have a larger voice because of your membership, to depoliticize and neutralize the conversation.
Thank you. Thank you for the input. So there is another question here about the more specific to South Africa, because it says that the South African government is notorious for not funding or supporting startups after investing hundreds of millions in R&D. And how confident are you as a research leader that the research community in South Africa isn't just again doing the intellectual research legwork for other interests with ultimately no real benefits accruing to the stated beneficiaries, which is the jobless youth, as you hinted?
Yes, it's a good question. And the answer is that we have changed our mindsets a little bit. So we do not believe that it is the government's role to fund from the very beginning all the way to the very end. Our view is that the government funds the de-risking stage to verify the science and to begin the technology development. But then it's for the commercial sector and the venture capitalists in South Africa to fund the transition from the technology to a company and onto a large enterprise. So that is why we're putting as much effort into the partnerships outside the university, outside the School of Physics. And the good news is that these partnerships are really maturing. We have lots of venture capitalists who contact me at least once a month, asking about what's happening in the quantum world, who's doing what, are there any investment opportunities. So we have to change our mindset that in South Africa at least, and I think this is true for most of the world, you cannot expect the government to fund it from beginning to end. They have their role to play, and then the other role players must step up and take their lead.
Thank you. I guess other countries from the global south should learn from South Africa, because venture capital is not that common, you know, in the global south, I would say. So let me see, because there are several questions and they are moving. Someone is asking for advice for you to orient them for papers that could be used to understand better your talk, I guess.
Oh, well, please email me. You should find my email without any problems online, or you go to Google
and also
Scholar.
Books. They are asking about books.
Well, okay, they can contact me, reach out, and I'll point them to some very good resources to get going on the topic. We love to popularize the field, so that's no problem to do.
So then I see two questions from students, basically. One is, what can the international community do to support early career scientists from South Africa to effectively prevent brain drain towards the global north? And then the other question is, how can students in physics education be involved or incorporated into the development of new, I guess that was an issue that Jean mentioned, that UNESCO is working on too, quantum education.
The brain drain is always a challenge because people will move to where there is opportunity, and there's certainly a lot of opportunity for quantum students and researchers out across the globe. I think the only thing that we can do, and what we are doing, is to try to make it attractive for people to come back. So we don't want to say don't go, but we want to say go, and once you have some experience, come back. Our emerging researcher program is one example of that. So we have specifically put money aside for the next generation of leaders. And if a university can identify such a person, we will give them a bag of cash to get them going and establish themselves at that center and become the next quantum leader. So we do what we can to make it attractive. I have to admit it is challenging to get people to come back, but a lot of people do want to go home eventually. And if they believe that there is an opportunity and they can be successful, then they will do it. So we're just trying to make sure that they know that there is an opportunity, and we welcome them to take it. As for the education side of things, absolutely. I mean, what we want to see, in fact, is that quantum gets out of the School of Physics. When that happens, then we know that we're successful. Every School of Physics has got many quantum courses, but we want to see it much, much wider than that. So we want to see courses in the biology department, in the School of Economics. We want to see the educationists come on board. As soon as it's not run by physicists, then we know that quantum really has taken off.
Great. Yeah, there was a question that said whether we should understand the laws of quantum mechanics to evolve our mindsets and sort of open to new degrees of freedom of thinking. Can quantum science help us change, think differently? I guess that's the question.
Well, I mean, certainly, yes. So in our own research in structured light, to try to identify these hidden degrees of freedom or these unusual ways to exploit light, we have very often taken quantum tools and translated them into the classical world, which has been enormously beneficial. And likewise, taking classical tools and brought them into the quantum world. And this idea that the two worlds are very disparate, I don't believe at all. I think there's a gray area where you could benefit from one another and learn a lot. So yes, we find that the quantum thinking helps you in structured light tremendously beyond just quantum.
Thank you. Then we are approaching the end. I would add this question, which is, what are the ethical considerations for quantum design that are priorities today?
Quantum design.
Yeah, well, I guess quantum technologies.
I know that
Are there any ethical considerations?
I think I've sat in a few meetings, and it's popping up more and more often about quantum computing. Should it reach a point where it can be used for nefarious means? Should we be restricting people's usage of the machine? I haven't seen any concrete proposal that's come out of such discussions, but it's certainly very topical. If you just Google, you'll find many, many white papers of different perspectives on the topic. In South Africa, we are engaging very strongly with the legal departments, the School of Law, to look at what sort of legislation does South Africa need in order to be quantum ready. So for instance, do we need a piece of legislation that says when a quantum computer can decrypt at a certain level, you may not call your banking secure unless you have this quantum layer underpinning it. So we're looking at the legislative side, but I agree that there's also a very strong ethical side. I don't have the answer yet, but it's definitely an ongoing conversation, and we're definitely very, very interested in watching where it goes.
Okay, so there are other questions, but I think we are approaching the end, and there are some specific questions about your research that maybe people can submit you the questions by email. And so I leave the floor to Christine to wrap up the session and say a final words. And I thank you again, Andrew, for the beautiful talk and the very insightful answers to these questions.
Yeah, so thank you very much. It was, I think, for the question and answer session, very, very instructive as well. We have a few more questions indeed that may be answered later as well by emailing you directly. I think it would be the best way forward. And then to read and watch again the recording that will be available is in 1 or 2 weeks from now, so on the webpage that we gave just before us. And indeed, this joint collaboration with UNESCO so is very, very important and valuable for such a question, looking at this quantum and how with this sustainable development and all the climate change we could have an impact. So this is this multidisciplinarity also that you reflected to, that will show us that society will change thanks to quantum and putting this revolution so in the right path. So this is what we want to do. So thank you very much for everyone also to listen, and we are right on time so to finish so this session, and we give you so the rendezvous for September, so with much more question and answers and forum and engagement, but still on quantum. So thank you everyone, and please let's stay tuned. And thank you, Andrew.
And sorry for those of you that I didn't have the time to ask your
Thank you very
question.
much, everybody. Thank you.
Thank you. Bye-bye.